Okay, so in this video, I'm going to show how to select profiles in ArcGIS or ArcMap, actually, um, along a fault scarp, a normal fault scarp, and then extract those profiles to text files that we can analyze in uh, a profile tool developed by the USGS to determine the vertical separation across the normal fault from the hanging wall to the footwall. And so for this example, we're going to look at the North Genola Fault, which is an area that student Kristen Smith has been studying here at Utah Valley University. And so we dug a trench site here where this yellow polygon is located. And you can see this fault scarp runs all along here, this provo bench / fan delta feature. But there's some differences along this fault scarp. We can see here it's crossing a Holocene alluvial fan, and we can notice the scarp through there. So we'll profile here. We'll also profile this inset fan scarp and this higher surface fault scarp across a few places to see what the variances in the displacements are. Can we see evidence of different earthquakes on different age geomorphic surfaces? And then can we see variances within the same geomorphic surface that show us something about the distribution of fault slip and how different that is along the fault? Okay, so this is to kind of help students that want to learn how to extract profiles and analyze them in a Matlab script developed by the USGS called Scarp VS. Okay, so here I'm using ArcMap 10.8.2, I believe. And so this is roughly the same area that figure that you just saw before. And so we're not using ArcGIS Pro because it's just simply easier to extract these profiles in ArcMap. QGIS might be a great way to go as well, although I'm not going to show that in this tutorial. Okay, so I have open 3D Analyst tools. To get that to be open, you go to Customize. Make sure your extensions are all turned on. The extensions are all turned on, then we will be able to add it by going to Toolbars and checking 3D Analyst. You'll also want the Draw tool to be open. And I always kind of have these other ones, but we want 3D Analyst, we want Draw tool, and Editor as well. So this is the drawing tool here. This is going to allow us to take those topographic profiles that we make in the 3D Analyst tool and turn them into features, actually GIS features that we will be able to save and name for later and display accurately in their positions in figures that we make. And then the editor toolbar is sitting here. That's because we're going to make those real features, then we're going to edit them and give them names. Okay, so there's a few ways that we could go about doing this. When I talked to my students as we were setting this up, I was saying maybe we should do one profile at a time, make it a feature, and then edit it, give it a name, so on and so forth. But actually, I think it might be best to make all of the profiles first, select them all, turn them into one feature class, and then we can edit them and give them each names across this site. Okay. So that's what we'll do. So I'm going to start fresh. So there's our trench study area. We have this high Provo level of Lake Bonneville bench. We have an kind of inset feature within it, which I think is like post Provo level, cutting in there, so younger. And then we have a younger surface in this fan and even younger part of the fan. But we can see displacement kind of showing up in that probably Holocene age feature. You can see displacement here in this older but younger than Provo feature, and we're wondering how consistent that displacement is on the Provo feature. So let's go and make sure in your 3D analyst, you have to set up your target layer is your DEM. You want to profile your elevation data. Then you draw profile lines, you click that, and you're going to want to do this a little bit iteratively. We're going to sample throughout this surface, but each profile we want to make sure is a good one. Okay, so I'm not going to go where we go down to a lower surface here, but I'm going to keep it in this surface. And so I'm going to just start as I draw these from north to south. And so I'm going to try one here. And I'm going to go roughly perpendicular to the scarp and draw it like that. Okay. And now I'm going to look at the profile. And so I feel like I have got a pretty good surface on the lower and upper sides of the fault scarp. There's some back rotation into the fault zone, but I think I can see two surfaces that I can match up across the fault. So I'm going to say that's a good profile. Okay, so I'm going to make another one. Just go along here and something similar right here. And again, I feel fairly good about that profile. So I'll call that good. Here I'm going to go near the trench. Our trench is fairly perpendicular to the fault, but you can see this is kind of an arcuate area of the fault scarp. So this might be a little different than what we draw here. That gets challenging in that area. But I think, yes, that could be one. Let's run a couple more and decide what we like. If I run one closer to what the trench looks like, let's see what that looks like. Yeah, so these upper and lower surfaces aren't going to match up perfectly. We don't have a lot of lower surface to see. Okay, so since these are all these lines that you're making are just temporary things, you can delete them with the draw tool arrow. I didn't like that first one. This one might be okay, but let's see if we can do better. So I'm gonna like this. So the lower surface, because it starts to feel this other escarpment, and it's pretty flat. So this is going to be an interesting displacement. This one was closer to the trench, and we're going to compare to trench offset. So I think I'm going to keep that one. I'm going to delete that one. The color of these lines, if you're like not liking that, you can almost change the line color here. These to all be black, just so we can see them similarly. No problem, under the draw tool. Okay, so I don't need to keep my profiles open once I'm satisfied with them. So there's 3 there down near the trench. This surface has got some modification by humans. You can see piles here, some excavation here, but I can see a bit of surface right here that might be original. So let's try one right here. Oh, still got that color, but that's okay. Yeah, I think that will work. That's as much of the surface as I have. Gonna change it back to black. And so we got 4 on that surface, 1 over here. I wonder, it might be worth trying one here. It's a little tricky. Yeah, let's try that. Black as well. Okay, so now I've got 5 different profiles to analyze on that surface. Let's see if we can do 1 or 2 on this across this inset part of the surface. So here it's a little tricky. There's not a lot of space to deal with, so let's that. That looks pretty good. Save that one. Can kind of analyze them a bit more later. I'll do one more. Ooh, that gets a little funky. But I might be able to see what's going on in there. So yeah, we'll save them for now. I just don't think I'm going to do a lot better. Make those black as well. For consistency. Okay, use the hand tool. Now I'm going to go down and see if I can see any displacements in the younger surfaces. So here's my escarpment, the fault that I am interpreting. And I can see there's an older part of this fan kind of preserved here and then a younger, and you can sort of see something in this part of the fan here, which I could try to go for. It's near a road though, so you gotta be careful. I think I can see that. It might be modified. Let's do one more near it. Maybe on the other side of the road I should have tried. Let me try this one. Now that looks uninterpretable. It's also possible that the fan deposited over the scarp and is draping it. So we might get slightly different results here, although that does not look bad. So I'm going to use those two on that youngest part. And then it seems like I might see something here even. But there's some changes in aspect there, which are tricky. Don't think I like that profile. There's kind of a similar color and aspect in this orientation. Let me try across that. Yeah, that's a pretty broad scarp, but I can see it in there. I'll try that. And maybe try one more. Right here. It's a steeper fan, or I don't like that one. Okay, so I'm going to call that good. So I have 3 in these lower surface, 2 in this medium surface, and 5 up there. For OCD purposes, change those colors. And let me continue to shift select all these. Okay, so they're all selected. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so 10 profiles. Now in the drawing tool, we can go and convert those profile graphics to GIS features. So I'm going to use the data frame, which I can see is in NAD83, UTM zone 12. And I'm going to save these where I'm going to be doing the profile work, which to navigate to. Oops, it's under the students files, Veronica and Parker, Genola North fault example. And I'm going to call this West Mountain fault profiles, fault profiles. Okay. And I'm going to delete the graphics after they are turned to features, and they're going to appear here as well. Okay. Yes, I want to put them on the map. Now they're all there. I could change them and prove it to us by giving them a different color. There's our profiles. West Mountain Fault profiles. Now, if we open the attribute table, can see the good thing is they're all labeled as polyline ZM, which means they retain their profile information from what we drew. So if I select one, get the select features tool, I select this, I click the profile, it comes up in the 3D Analyst tools. So now what I'm going to do is I'm going to start editing. I'm going to click on West Mountain Profiles, and they got an ID number. I guess they started from south to north, or in reverse order of how I drew them, not south to north. And that's fine, but what we want to do is give them a real name. So we'll call this, I guess in this case, I will go from just the site. I will kind of name them related to the geomorphic surface they're on, and then the order from south to north. Okay, so this is so site West Mountain S surface 2 second youngest surface P1 profile 1. Enter. Bigger so I can see it. Okay. So then click the next one. Okay, so no, the next one is this one. So this would be West Mountain surface 1. This is the youngest, lowest surface, profile 1. The one above it would be the northern one, so profile 2. So West Mountain surface 1, profile 2. Okay, and then this one's West Mountain surface 3, profile 1. Next one, go and select it to make sure. Yes. West Mountain surface 3, E2. And then these should all be in order. So I think I'm confident in that. No, I'm not. Okay, that's the lowest one. So West Mountain surface 4, profile 1. Then it's going to be profile 2 here. West Mountain surface 4, profile 2. And West Mountain surface 4, profile 3. West Mountain surface 4, profile 4. West Mountain surface 4, profile 5. Okay. So those should all be correct. Let me save the edits. Let me stop editing. I'm having trouble getting my labels to show, but let's see if it will show up. Label features. Not sure what's going on here. Must have something in the labeling preference it's turned off. Label using name. Some properties. Yes, not showing up. No problem. I kind of know how I ordered them, so I'm okay with that for now. But it would be nice to label the features, because then in this next step, what we're going to do is export the profiles. So if we select, so they will start with the surface 1. So if we go here to surface 1 and select that feature, we can make a profile graph of it. And then in the profile graph, you just go not save, but export. And we're going to go export data as a text file. In the text file for the Matlab software that has been written that we're going to use, it doesn't want any labels or headers. It just wants the X and Y data. So we're going to turn those off. We're going to choose text file, and we'll click save. Should give us a place to save them to. So I'm going to navigate to that same folder. Mentoring. Veronica and Parker. Genola North Fault example. And then I'm going to label them exactly how the features are labeled. So surface 1, profile 1, and then click save. Don't have to add the .txt, it'll show up there anyways. And then the interesting thing is, well, it's done, it's saved, but it doesn't get rid of the dialog because you do other things if you want to save it as another file type. But we don't need to do that, so I'm going to click close. I'm going to turn this off. I'm going to change my selection. So I think I've got my selection tool, such as, well, I can make a rectangle, but if I click, it makes a new selection, doesn't add to the current selection. That's good. That's what we want. Okay, there's the next one. Export data, text, turn these off again, save. It remembers our folder, so I can click on it and just change it to profile 2, save, close, close. New selection, go to surface 2, click the profile, export, data, text, uncheck these boxes, save. Now, profile 1 of surface 2, save, close, close. Surface 3. Ooh, that one's going to be weird, but okay. Export, data, text, check the boxes, save. Surface 3, profile 1, save, close, close. Select the next one, create the profile, right click, export, data, uncheck the boxes, save, profile 2. So I'll continue doing this. Now you might ask, well, why not select all of these and make the profiles and continue? See what happens when you do that. Well, it puts them all on one output, which is interesting, but it's not going to work with the way that our data is loaded into our Matlab script. So we're not going to do that. So I'm going to close that, clear selection, go back and select this one, create the profile, export, data, check the boxes, save. Surface 4. So another thing, if you look at this profile, you might say, okay, well, it's much longer on the lower side than the higher side. What are we really correlating? In the software we're going to use, we'll be able to zoom in to the part of the profiles that we want and exclude parts that we don't want, say like up here. And so don't worry about that. it's a good idea as you're doing this sort of stuff, take notes. Like I called the highest surface profile 4. And some people may go in the opposite direction. 1 is the oldest, and you just keep going until you find younger surfaces. Write down what you're doing so you remember if you come back to it like 2 months later. That's how I usually operate, so I know I'll remember it, but always good idea to write it down. Okay, so that's all done. And if we look in our attribute table, we've got our files with our names. And I believe I saved those in the same folder. It's a good practice, probably. So if I go to general source, Dropbox, teaching, yeah, Genola North fault example. So all that data is there. We have the locations of those fault profiles. We have all the profiles extracted. We have the right names on them. We're ready to go. We're done with Arc Pro. You could save your project and move on to Matlab. So let me pull up Matlab. So I've already got that Matlab open. I'll also open up a tutorial. So the script that we're going to use is called this Scarp _VS. It stands for fault scarp analysis vertical separation. It also calls this slope angle function. So to run the script, you need both of these .m files in the folder that you're working in. And so in MATLAB, we need to set up the file structure so that where we're operating, extracting the files, the profiles are located there. So if we open that, and the profiles need to be set up so that they only have X and Y positions. If you read through the tutorial, you can see that they can be absolute or relative positions. In this case, the vertical is absolute, but the horizontal is a relative position along the LiDAR data. This is fine. If you have stuff above that, it will confuse it. So you have to either comment it out or delete it. We already deleted that, or didn't add it. We're not going to read our shape file, but you can see it through this lens. And yeah, so this tutorial, supplemental text instruction for profile vertical separation code, is quite helpful. Make sure you have that handy as you're doing the work. And so just a reminder, all of this is, let's see if I have, this is coming from a paper with the primary author is Christopher DuRoss from the U.S. Geological Survey, studying vertical separations of along a fault called the Lost River Fault, which last had an earthquake called Bora Peak earthquake in 1983, and had a prior earthquake to that as well that's shown nicely in the geomorphology of the site. And so the group, which includes myself, we flew basically drone imagery across the fault zone and turn that into digital elevation models through automated photogrammetry using Agisoft PhotoScan. So we have really high resolution TEM, just multiple centimeter scale in the horizontal, and really high resolution in the vertical. And so we're able to analyze multiple events of earthquakes and their displacement along those events. And so the USGS made this nice Matlab code that you can use, and you can get that if you go to their, basically their publication allows you to download that as a supplemental file. And so here's the instructions for it. Okay. So I'll keep that open over here, zoom into it a bit in case we want to reference it. So here we have our MATLAB window, and we could open the Scarp these _VS file, just see what it looks like a little bit. There's 650 lines of code. And so just for your reference, percents are areas of comment and out. You can see at the top of the code, they are clearing the kind of memory of the program. They're defining some matrices that we're going to fill in with data. But basically what happens is we'll run Scarp VS, and it'll ask us which profile we want to look at and analyze. And from there, it's very just graphical user interface. But at the end, we'll be able to potentially interpret the vertical separation using different lower and upper slope profile interpretations, and then get a statistical analysis of what that vertical separation is, depending on multiple interpretations or single or preferred interpretations of that profile. Now we've got multiple profiles through the same surface, and we might have multiple interpretations. In the end, you could then try to, what's the displacement across this geomorphic surface? We could get a plus or minus on that really nicely with all of this great data. Okay, so what we would do is lowercase run space, and then just call scarp _vs dot m, boom. Okay, so you can see that it brings up a dialog box, and I'm going to basically run a few of these on, I'm just going to do the S4, the upper surfaces, just so we can see some variations through there and see if we get different results. Okay, so what you do is you just click the one you want to start with. So I'll do S4 P1, say open, take a minute. Oh, goodness. It spit it out on another screen for you. So let me say, let's say no, okay. Okay, so now you can see basically what pops up. So you get a figure to look at, which is on the bottom, the XY profile. And I don't believe there's any vertical exaggeration. So that's why it's low, like kind of low relief like that. Then above it, you see kind of slope interpolation between the points. And so you can see areas of consistent slope, the steeper slopes of the fault scarp, and back to consistent slope again up above. And so what it asks you to do is, if you want to subset things, like maybe I didn't want to look at this long tail over here, you could zoom in to what you wanted. I didn't subset anything. You can also exclude things, like say your LiDAR data went over a big boulder or something, you didn't want that data point to show up, you could exclude it. And so it gives you those options. And with those options, you're going to do the same sort of method. Basically, just click to remove parts that you don't want to remove, or to select the parts you want to subset to. So, but here we've moved past that. So the first step is to analyze the profiles. Click twice to select points to use for the lower far field slope. So I say I have to click OK. And then I'm like, okay. So you can kind of see the far field slope keeps hovering between like 0 and 3 degrees. And so I kind of like maybe this point to somewhere about this point. Okay. Get it? Okay. So now a new dialog has popped up and it says click twice to select the upper far field slope. So I say okay. And now you can see it goes back again to like 0 to 2 or 3 degrees. So you don't have to click exactly. It's more about the X position. So that all looks good. So then you can see it kind of projects those back into the Scarp, and you can see kind of a potential offset there. But we have another message which says click twice to select points to use for Scarp slope, because that's also part of it. Okay. So I'm going to say that the Scarp starts kind of about here. To about here. All this is coming up here on another screen. So I basically, once you're happy with it, you can say, and so you can see it estimates 2.51 meters of vertical separation. I said, yes, I was happy for that estimation. I want to keep it. And then I need to give it a profile version. So I'm labeling it West Mountain Surface 4 Profile 1A. Because I might do multiple iterations of this one. So I'll say, okay. Then it asks me, is this your preferred vertical separation? I'm going to say not sure, so I'll just say no. Okay. And then it asks me, do I want to rerun it? And I'm going to say, okay, yes. It's kind of annoying. It keeps showing up on this other screen. So I'm wondering if I can maybe switch which screen I'm sharing so you can see this better. So I'm going to stop sharing. I'm going to share other screen. And so hopefully now you can see, okay, so it's reopened the profile and it's like, do you want to subset the profile? In this case, we'll try subsetting it to see if that ends up giving us a different result. So now it says click twice to define a profile subset. So I mostly want to trim the upper side, but I'm also going to trim a little bit of the lower side. So we're basically gonna oh, I forgot to click OK. This is a classic thing. So if it's not clicking, it says click twice to define the profile subset. You need to say OK to that. Then you'll get your crosshairs. OK. So now I'm going to go from here to maybe about here. Okay, so now it's zoomed in. It's more symmetric. I'm not going to exclude part of the profile. So I'll say OK. Click twice to select points to use for far field lower slope. So now I can see it's consistent from here to here. So that's kind of what I'll pick. Now for the upper slope, gets consistent out maybe here, right? The root mean squared error is a little different than before, so we're probably going to get a different result. That's good, because we want some statistical kind of analysis here. Scarp slope. Okay, so now I'm kind of like, So it's where it gets steeper. Maybe I'll try to do more of it this time. Okay, this time I got 2.47. Last time it was 2.51. And it's showing up more accurately here, the vertical separation, nicely shown there. I want to include the result. Okay. And I think I want to call it West Mountain S4 E1B. Okay. And yeah, I'll call this my preferred one. You want to try it once more? Yeah, why not? What do I get if I do this again, but say maybe I just trim down what I'm looking at in the Scarp slope. Okay, so I'll run it one more time. Subset it. Okay, yeah, let's do it. Oh, I said no. Okay, I won't subset. I won't exclude any parts. Select the points for the far field slope. So I'm going to be fairly consistent. Upper slope. I'm not going to go all the way out. Well, sure, why not? Let's go out pretty far. Just to be different. Scarp slope. So now maybe only do the steepest parts. So from 8 degrees and above. Now I get 2.51 again. Profile. Maybe I don't need to do this. West Mountain S4 P1 C, but I am. Okay. Is this your preferred one? No, I said it was not. So I say, okay, rerun it. I'm going to say, no, I'm done now. Save results. Yes, I absolutely want to save my results. Text to be appended to the file name, i.e. version 2. So it puts the input file name and then it gives whatever you write here. So I'm going to say, here I'm going to say, Tokay, I did this, and I'm going to give the date, 6/27/23. Just so I know who did this, say if you're working in multiple groups, and when did I work on this, in case I want to go back to my notes if I've been taking them. Okay. And then it asks, do you want to prioritize report the preferred, mean, or midpoint? It defaults to preferred. I'm going to do that here too, but it will also show you all this stuff. So in case you change your mind later. Okay, so let me change what I'm sharing with you again. Stop sharing, share the other screen. Okay, so now it created all the matrices. It output the summary information. So if we look through here, you can see regression statistics for each of those iterations that we went through. You could save this, but you don't have to save all of it because most of it's saved in these two files that are created right here. So you see it's West Mountain Surface 4 profile 1 underscore, and then that appended Tokay 6/27/23. And then there's an individual and a summary file. If you go down to the end of your explanation file here, we can see that the summary file includes the preferred, mean, midpoint, whatever you selected, depending on user selection for the reporting, the minimum vertical surface offset from all, the maximum being profile length, far field slope, upper slope, Scarp slope, number of iterations. And so that's the summary. So if I open that, we can see it. It gives way too many significant digits. These are in units of meters and scientific notation. So like you can see my profile length was on average 60 meters long. But then these are in, my preferred was 2.46 meters. I might round that to 2.5, given our uncertainties of things. Not a lot of difference here, 2.5 meters. Okay, so that's in the summary file. In the individual file, you get a bit more. So you get basically each iteration of what you run, those same things. So you get the recorded profile length, the lower far field slope, upper far field slope, Scarp slope, and whether or not it was selected as the preferred interpretation. Also, all these matrices and figures are preserved. So I can open up my preferred figure, and I can open up my preferred matrix, and it'll tell you even more. That will be saved as well, I believe. So yeah, if it's not, you can export those things if you're seeing that that's not saved. So if we open back up the figure, you could either screen cap it or copy the figure, put it somewhere, save it. You're probably going to want some of those for your later graphics, for sure. Not that we can't take those profiles and open them up and redo them again. It's a pretty quick process. Okay. So now I'm done with that one. So if I wanted to do another one, I would just type run. Actually, well, you can just press the up arrow because the last thing you did, find run Scarp VS. Boom. Gonna start over. Now it's like, okay, which one do you want to look at now? And you can see the appended files, which one we already did. So let's try the one that's by the trench this time. So here that one is. So I have to somehow select the points for the far field slope. And so really to do this, when you have a different slope on the hanging and footwall side, you kind of need to be careful and remember the geomorphology of the site. So I know at this site there was like a road constructed on the upthrown side. So this gets a little low slope there, which is similar to the low slope down here, but you can see just this back rotation of the surface expressed in the slope here. So yeah, projecting through this one is going to be tricky. I might need to do a few iterations. So first, I'll just be really non-committal, and I'll just select everything on the downthrown side and everything on the upthrown side and see what happens. So I'm almost going all the way to each end. Okay, now go for the up slope. So get off the Scarp. Okay, so then they come in through there. And where's the Scarp? The Scarp is probably most strongly through this area. So that gives me 2.4 meters of vertical separation. If you remember, we were getting 2.5 before. So, that's not a bad measurement. So yes, I will definitely include the result. And I'd call it West Mountain surface 4, profile 3, and yeah, and then A. Is this your preferred vertical separation? I'm gonna say I don't know, and I'm gonna rerun it. See if we get something different. Okay, so here it is again. So for the lower slope this time, I'm gonna try to not go into this back rotated part. And so I'm gonna try to go out. Oh goodness, I did that wrong, I think. Let's see. I selected in the opposite order, but I did select 2 points, so I think it can count for that. And then the upper side, I'll also stay closer to the Scarp. Now this is going to give me a way lower vertical separation. Now the Scarp, and it puts them like not even where the Scarp is, right? So Scarp is here. So now this gives me 1.8 meters of vertical separation. I will include this result. I'm definitely going to say it's not my preferred result. And the reason for that is I know from the trench offsets of soils that we saw that are buried, we can see it's closer between 2 and 3 meters, right about 2.5 to 2.7, I think. So, yeah. Not my preferred one. Yes, I'll rerun it. Okay, so let's rerun it. Let's try to get a preferred one here. So lower far field slope. So I feel like another thing that's happening is we're getting some steepness here because it's rounding off to the next escarpment. So I'm actually going to go further over here. It's more consistent through this zone. So I'm going to say this is my lower slope. Now my upper, yeah, where this gets to that low point, I'm going to again go all the way through here. Okay, the Scarp slope. So here it's 10 degrees. Here it's, I'm going to go from this point, oh, this point, this point. Okay, so whoops, I was clicking on the slope and it works, but for whenever when I do that, clicking up there, it puts it here instead of down here. Um, let's redo that. Okay. So I said we're gonna off of that. And I was gonna do the whole thing here. Then I was going to make sure I'm clicking in here. Okay, so this gives me more. This gives me 2.6 meters. And I will include this and name it. And I'm gonna say that it is my preferred one. It matches what I saw in the trench better. And I'm not gonna rerun it. And I will save the result. Number one, that's the key thing. The default is to not save the result. You don't want that. Okay, so the text that you're gonna append, again, toke underscore 6, the date, 2723, and it will have the file name in front of that, so don't need any more specifics. And I'm going to use the preferred. And so there it is. It shows up here now. Profile 1, profile 3 have been done. And you can see what other ones are remaining. And so if I click on the summary, 2.6 meters. The other one was 2.45 meters. Pretty similar results. Okay, so maybe for fun, we'll rerun this once more, but this time we'll do a different surface. Let's go to surface 1, the youngest surface, to see what we get from a really small displacement. So I'm going to run Scarp yes again. Surface 1, try profile 2. And I'll just try to do this once. I'm not going to subset it. Okay, so here's my profile that popped up. And so you can see it comes up to this zone of possible faulting. Right, and here it gets 10-degree slopes. And then back here, bouncing around. These are steeper slopes because we're on a fan. Previously, we were on a lakeshore feature, or kind of hybrid between a fan and a lakeshore sleep feature. So anyways, yeah, we need to kind of take that into account. Okay, so lower far field slope, I think I see, it's kind of this 5-degree zone here. So I'm gonna select that. Okay, for upper far field slope, now I go back to this kind of 5-degree zone here. Okay, so you can see the Scarp the displacement's going to be much less. It's twice to select points for the Scarp slope. It's basically right through here. This only gives me 0.42 for displacement across that. I will include the result. And let's rerun it. This time I'm going to zoom in. So it says click twice to define the profile subset. So zoom into there and to maybe here. So now you can see a little bit more detail, which might help. And so lower far field slope. So here's my Scarp. And so I'm going to say right here. I'm just going to deal with maybe to there. Okay, for the upper side, get off the Scarp. I'm actually going to go way up here. Okay. So this gives me quite a different result, 0.7 meters. And so I was assuming basically here that, I was just trying to look for the really lowest slopes on up and down thrown sides, um, projecting across a scarp that might have diffused quite rapidly because it's steep and it's loose. And so I think this is, yeah, I'm going to include the result on version B. I am going to call this my preferred one. I think I was pretty careful about that. So, and I'm not going to rerun it right now. And I'm going to save the results. Yes. And I'm my name, Tokay 623, 627, 23. I'll use the preferred. Okay, so that means that, in the last earthquake, probably, unless this is a modified scar, you know, there of the 2.5 meters of displacement on an older surface, point like 0.7 meters is from the most recent earthquake. And we believe from the trench that there's only 2 earthquakes in there. So that means it's a kind of smaller earthquake, or it's more distal on the slip distribution than the prior earthquake, which would have been larger on the older surfaces, as we see there. Okay, so close this. And now we can see, yeah, we've saved a figure from each of these, which is nice because we might want to put that into an overall figure later on. Okay, so I think that is a good enough tutorial for now. So I'm gonna go ahead and end this video. It's over an hour long already. So hopefully this is helpful. Let me know if you have any questions.